This question is about equilibrium constants, specifically Kp. 0.102 grams of solid ammonium sulfide is heated in a closed container at 100 degrees C until equilibrium is reached at a pressure of 0.1 megapascals. Notice how they have given us a temperature. This is because equilibrium constants Kc and Kp are dependent on temperature. Constants Kc and Kp are dependent on temperature. Kp is not dependent on pressure, but we will need this to calculate partial pressures later. Partial pressures are the total pressure times by a mole fraction. Masses can be converted into moles using number of moles is equal to mass over molar mass. We can now think about the species. The ammonium ion, NH4+, is seen in lots of ammonium salts. The sulfide anion has a 2- charge. If we combine these together, we need to add additional hydrogen to ensure our overall species is uncharged. We were told in the question that ammonium sulfide is a solid, thus we should give it a solid state symbol. It is dissociated into two products. Firstly, ammonia gas. Secondly, hydrogen sulfide. Counting the number of nitrogens on each side, we see we have a balanced number of nitrogens, 1 and 1. The number of hydrogens on this side is 5. On this side we have 5 also. There are 1 sulfur on this side and 1 sulfur on the right-hand side, therefore the equation is already balanced. The coefficients in front of each of the species are 1, 1 and 1. The first row we will construct will be the initial masses. Since these are products, they have no mass initially. We were told in the question the initial mass of the solid ammonium sulfide is 0.102 grams. I mentioned that we need to convert this mass into moles using our equation number of moles is equal to mass over molar mass. To work out the molar mass, we must refer to the periodic table to find the molecular weights of each of the atoms in the molecule. The AQA data booklet gives the masses to 1 decimal place. We have 14 from the nitrogen, 4 hydrogens, a sulfur and another hydrogen. This gives us a final result of 51.1 grams per mole. Subbing in our mass over our molar mass, we find that the number of moles is approximately 2 times 10 to the minus 3 mole. Note how the grams cancel each other and the units of per mole in the denominator become mole in the numerator. We can now fill in our second row, initial moles. Referring back to the question, we see that the system reaches an equilibrium when the pressure is 0.1 megapascals. It's found that 75% of ammonium sulfide has dissociated. That means that only 25% of the ammonium sulfide remains. 75% of it has been converted to these. It is 75% of the number of initial moles that we are talking about. 75% of 2 is just 3/4 of 2, so we can write 1.5 times 10 to the minus 3 has been converted into each of our products. Since only 25% of this remains, we can say that there is 0.5 times 10 to the minus 3 remaining.
This is our third row, moles at equilibrium.
We can also write this out in terms of percent. We started with 100%. Then we ended up with 25% because 75% had been taken over to this side. Now we add the moles at equilibrium to give the total moles at equilibrium. Stop! May I have your attention, please? This is an important piece of information. The total number of moles at equilibrium you might think would be 3.5, but because the ammonium sulfide is a solid, it is not counted in the total number of gaseous moles. Therefore, the molar fractions for the ammonia and hydrogen sulfide are 1.5 divided by 3. The times 10 to the minus 3's cancel because they are in both the denominator and the numerator. Therefore, the fraction can be just written as that. This leaves us to calculate the partial pressures, which are going to be half, or 0.5, times by the pressure that we were given in the question for total pressure. We can see, just by looking, that would be 0.05 megapascals. The Kp expression can be written in this form, where each species' partial pressure is raised to the coefficient in the balanced equation. Note that they all must be gaseous, and the product partial pressures are in the numerator, whilst the reactants in the denominator. Here, the reactant is a solid, so it is excluded from the Kp expression. The partial pressures of our products are on the top of the equation in the numerator, so it's simply timesing these two together. The units are megapascal squared. Since we timesed a unit of Pascal by another unit of Pascal, the mega is just a prefix. The final result in standard form can be written 2.5 times 10 to the minus 3 megapascal squared.